full example, and it's closely related to your homework. So what we're going to do is we're going to solve the Laplace equation or diffusion equation on this rectangular domain. So this is a subset of our model problem. What we're going to do is we'll use 6 rectangular elements. So this will be element 1, element 2, element 3, element 4. Wait, sorry. I drew too many lines. Okay. So we'll have 6 elements. Okay. 1, 2, 3, 4, 5, 6. We'll have the global node numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Each element will have the local node numbers 1, 2, 3, and 4, and have a width A and a height B. The boundary conditions will be u equal to 0 on the right-hand side, and this function u equals u of 0 cosine pi x over 6a on the top. So that's like a cosine function that is, at the left-hand side, it's u0, and then it comes down to meet, to be 0 at the node 12, right? So it's like a piece of a cosine function, right? So we'll go back to this that we derived earlier because we can use it. We already derived the element stiffness matrix for an element stiffness matrix that has a single data on the diagonal, k, a11 equals k, a22 equals k, and then on a rectangle that has a width a and a height b, right? This is our element stiffness matrix. So what we need to do next is we need to create a connectivity array. And so I got to basically do that myself. I'm just going to read off, again, just starting with element 1 in the notes. I'm going to start with element 1. I'm going to read off in order from the lower left-hand corner to the lower right-hand corner to the upper right-hand corner to the lower left-hand corner. I'm going to read off the global node numbers, okay? And I'm just going to write them down as I go. So I'll have 1, 2, 6, 5 for element 1, 2, 3, 7, 8 for element 2, 3, 4, 8, 9 for element 3, Element 4 will be 5, 6, 10, 9, 6, 7, 11, 10. Element 6 is 7, 8, 12, 11.
That is 2, 3, 7, 6, right?
2, 3, 7, 6. Thank you. Anybody see any other mistakes? It's gonna make a big difference. So element 3 is 3, 4, 8, 7. Thank you. Element 4 is 5, 6, 10, 9, 6, 7, 11, 10, 7, 8, 12, 11. Okay, so got my connectivity array. I need to allocate my global stiffness matrix. So my global stiffness matrix will be a constant array of zeros that is 12 by 12, right? Because there's 12 unknowns total. All right. So then what I'll do is I'll say, I'll use a loop that I'm going to loop over all the nodes. So I goes from 1 to 12, and K connect I connect I. What do I call that up there? KE. KE. Oh, sorry. This goes from 1 to 6, the number of elements, not the number of nodes, right? So that's what my global stiffness matrix looked like, what we can see on the screen. Okay. So now we need to form our right-hand side vector. So right-hand side vector, basically we need to apply the boundary conditions. So what I'm going to do here is I'm just going to, for simplicity and time, and I'm just going to make a modeling decision. So we just went through this whole exercise of like, how would you evaluate a function on the boundary, right? But the thing is, we already know, well, I have this function which is a cosine function, so it's going to be sloped like this, right? But my element shape functions are just linears, right? So I'm not going to be able to capture with a linear like perfectly that slope, right? It'll just be like linear, linear, linear. And so what I'm going to do, obviously, if I made the elements smaller and smaller and smaller, then I could, in a piecewise way, capture that shape. But so what I'm going to do instead is just for simplicity, and so I don't have to write the integrals and evaluate the integrals here. What I'm going to do is I'm just going to evaluate this function at the nodes 9, 10, 11, and 12. Okay, so basically x, that'll be 9 is x equals 0, 10 is x equals a, x equals 2a, x equals 3a, right? So, so I'll do that. So what I'm going to say is that f is a constant array of zeros that is also 12 elements. Okay, and so then f at node 9 is equal to u0 times the cosine of pi times x, well, times pi, well, I'll leave it as x for now, so that over 6a, right? And that's going to be evaluated at x equal to 0, right? That's node 9, okay? So then we'll just keep doing that for node 10, 11, and 12. So node 10 is x equal to a. Node 11 is 2a. Node 12 is 3a. Okay, so now if we look at what f is, right, looks like that. Okay. And then, of course, on the right-hand boundary, there's zeros. Well, since I initialized the array at zeros, they're already there. But I do need to make my stiffness matrix not singular, right? Basically apply the boundary conditions. So in that case, what I'll do is I'm going to have, there's a little trick I'm going to use. So I'm going to say, I'm going to use a sparse array. With a sparse array, then I just have to specify basically that I want, element 9 to be equal to 1 and all the rest zeros. So see how that works? So I get that. I guess I need to specify that the total array length is 12. Right? So I get element 9 is equal to 0, right? Well, then what I could do is, again, basically put this in a loop. So I'm going to loop, again, where I goes over the nodes where I need to apply boundary conditions. So 9, 10, 11, 4, 8, and 12. Right? So again, that comes from 4, 8, and 12 are 0, and 9, 10, and 11 are these sides. Okay, so I'm going to loop over those, setting the row of k equal to this thing. Right. So then I have k is equal to that, and you can see, like on the fourth row, on the fourth entry, there's a 1 there on the diagonal. And the other ones will be out here. You can't see them. All right. But now we have everything we need to solve it. And notice that this is all symbolic, so we can even have a symbolic solve, right? K, F. I say that, maybe. The algebra there. Yeah, it's ugly. Okay, let's put some numbers in instead. Okay, so well, maybe I can do it. So let's just say A is equal to 1, B is equal to 1, U0 is equal to 1. Is there anything else? Okay. K is equal to 1. All right, so those are the nodal solution. Let's see if we can make a plot of this solution. So I'm going to use this list contour plot. This is going to take me a second because I'm going to basically have to put out the X, Y, and Z locations of every node. So node 1 is 0, 0, UH, 0, 1. Then I have node 2 is 0. If A is 1, then that's 1, right? And then UH 2. That's node 2, right? Node 3 is 0, 2A, which is 2, UH 3. Then I have 0, 3, UH 4. Okay. Two more rows of that. Okay. So this is node 5 is 1, 0. Node 6 is 1, 1. Node 7 is 1, 2. One, 3. It's node 8. This is 2, 0. Node 9. 2, 0. Node 10. 2, 2. Node 11. 2, 3. Node 12. Okay. My parentheses are unbalanced. Oh, there it is. Here.
The first node is not closed.
Huh? Oh, it's not closed. That's right. Here too, yeah. I made that typo in the first row and then I... So let's, there we go. Did I transpose the... The plot looks transposed, right? Oh, I did. I transposed the X and Y values. You see that? Dang it. All right. I want to make it right so we can look at it. Oh. So 0, 0, 1, 0, 2, 0, 3, 0, 1, 2, 1. There we go. That's right. So, now I have a color bar. All right, so we expect the solution to be 0 on this side, and it is. Okay? And then, you know, cosine should be, at the left-hand side, it should be 1 with the values we put in, and it is. And at the right-hand side, it should be 0, right? And then it's like kind of smoothly graded in between. So that's the solution, right? And this is, you know, this is a pressure diffusivity equation, essentially. It's a steady state pressure diffusivity equation, right? If you had a cosine distribution of pressure on the top and 0 on this side, this is what it would look like, right? Any questions? Everybody understand how element assembly works then? With the connectivity array? Okay. So in the last 15 minutes of class, we're going to talk about another 2D problem, but this time